So the course you've all been waiting for. Yeah, so this is always exciting because, like I said, many of these students are here for forensic chemistry and you're going through all these other things and you're like, can't wait to get to that course. It also is a lot of pressure on me because I don't want you to be disappointed, You're like, gee, that was nothing like what I thought. And so, but I think, students in the past have said, yeah, it was a nice, different mindset on chemistry. This is definitely chemistry applied. Okay, so it's not just knowledge for knowledge's sake. And so we'll discuss more about what that means this morning. So what is forensic chemistry? Let's just leave it at this point. Well, I've got some things, but let's try to have some discussion this morning to wake ourselves up. Okay, so if someone were to ask you, your great Aunt Susan or whatever, what are you studying? And you say forensic chemistry. What's that? What are you going to say? Crime lab, okay? Yeah. So you hear that, but then, what is different about a crime lab than the water quality lab or TRIES over here, the environmental science lab? What's different about it?
High expectations.
Okay. Well, we think that, they would be really pissed if you said that to them, because they're testing your drinking water, right? And so that's cool too. We want high expectations for the drinking water. But you're right, this is going to be more challenged, I think. They send the drinking water report to me in my water bill every quarter or whatever, and I kind of glance at it, but I don't scrutinize it as if my liberty were online. If my liberty was going to be taken away based upon their percent, chloride in my drinking water, I would have a lawyer looking at that. I'll have my own experts looking at that. And so, yeah, as far as the level of scrutiny, the crime lab, the forensic lab is going to have a much higher level of scrutiny. And that's part of the discussion is this adversarial system we have to protect our liberties. Okay, we don't want to just send somebody off to incarceration and take away their liberty on a false positive. So there's this challenge system that we have. We have two sides that argue about the results. And so that puts a glove on our science. So this legal requirement is a sort of how we have to do the forensic science. And as with any glove, it has two purposes, or it has two effects, I would say. The purpose is to protect you. And so, yeah, our legal requirements are protective. They're not just protective for the defendant, if there is a defendant. They're also protective of you as a scientist, right? Because they separate you from the case, really. And so you don't get to know the people necessarily. You don't get to necessarily go to the crime scene and so on. You don't have an emotional connection to the results. So there's a lot of separation between you and the actual case so that you're protected from emotional concerns. I really don't like this creep. I don't know what the numbers say, but they're guilty. You've been separated so you don't even feel those tendencies, okay? And hopefully you don't know too much about the data that you're analyzing. So that's protective of you, but as with all personal protective equipment, like gloves, what do you lose when you put on a glove? Tactile. Yeah, you're not as sensitive, right? And so there are some ramifications to these legal requirements too. You can't just go on a hunch. I think it would be better run at this temperature, or my GC oven, is a little off, and so I'm going to adjust it some way. You can't do those things. You lose a little bit of that dexterity and ability to adapt because of the legal requirements. So that's essentially what the text says. It's qualitative and quantitative analysis. So those two words, qualitative is what is it, and quantitative is how much is it and how sure are you. So we answer those three questions in analytical chemistry. That's essentially analytical chemistry summed up in 2 lines. What is it, how much, and how sure are you? That's the quality control part, and the confidence intervals and things like that. And so it's analytical chemistry, but it's applied to the forensic, to the legal requirements and the forensic enterprise. So we won't necessarily answer that what is it all the way down. We may say this is a red stain, and we really want to know, is it blood or not? Not necessarily what is it. If we determine that it's not blood, we don't continue answering that question. We've got other cases to move on to. So it's not quite as, it doesn't follow analytical chemistry to its total end of total qualitative analysis. really you're just comparing. Does this compare to blood? Is it or isn't it? Or does this compare to some other forensically valid concern? You know, if it's a color spot test, is it the right red or not? You know, and if it's not, it's a negative result, and then you move on. So there's a lot of unanswered questions because, again, we're trying to just answer the legal questions, not necessarily the chemical questions. Make sense? And so then we have this identification, classification, and individualization. The easiest way to describe that is you might have blood. We identify that as blood. Classification might be blood type, okay? And then individualization would be DNA. So you have these broad categories, blood or not blood, you know, what kind of, you know, A positive or B negative, and then individual would be down to the person. And then the forensic part, that just comes from the Roman Forum. If you think about the societies, the Greek societies, and then really in its blossom in the Roman societies, civilization had reached a point where the daily needs for food and shelter had been taken care of. And so once that is taken care of, then you have this blossoming of other areas of society, like education, like universities, like the legal system and so on. And so this is the city gates or the Roman Forum. These are places where other disputes will be taken care of. And so that's where the part of forensic science came from, the Roman Forum, where they would debate out issues. So we have this range of high quality standards in science as a part of forensic science. But this is forensic chemistry. And so even in forensic science, you're going to have the biology side and the chemistry side. And we're just going to be focused in this course on the chemistry side. We'll study the quality part as the first third of the course. And then the second and the third parts of the courses will be on chemistry. So we will cover a little bit of toxicology. I call it baby toxicology. And so we understand how some of these drugs interact with the body, but we're not going to get into the DNA or the fluids of the body and so on. We might talk about them in terms of routes of entry or samples, you know, that we analyze, but we won't get into physiology or toxicology on an in-depth manner. And so here's the visual syllabus. I think the one that was on in the back of the syllabus still had last year's dates on. So these are the current dates, and you'll see it in the schedule. The schedule is accurate in the syllabus, but the graphical part I had not. I discovered that yesterday, so I made these changes. So these are the exam dates. Really, there's 3 exams equally spaced, and then a comprehensive final, so that you get 2 passes at the information. So if you mess up on exam 2, you'll see that material again on the final, so you can show to me that you got it. And then the homework will feed into all of those exams. So even though the homework is 10%, it's going to feed into the exam. So take the homework seriously and you'll do better on the exams, as you saw in PChem. We're going to do, instead of the accumulated points, and for those of you who had me in PChem year before last, or fall before last, don't know what I'm talking about. But those of you who just had me, who did the accumulated points in the fall, I'm going back to the average thing, to where no matter how many points we have on the homework, your homework grade will be your average of the total possible points for homework. That way those categories stay 10%, and the control chart is 10% and the exams are 80%. So again, the exams are the large chunk of your grade, but if you focus on the homework, you'll do better on the exams. And these are the main 3 parts of the course. At the top is the statistics and quality control. And so that's what we want to focus on initially. You have had some of this material in quant, okay, average, standard deviation, and so on. But we'll go a little bit further than that. We'll get into Pearson's correlation coefficients. We'll talk about a lot more about statistical hypothesis testing, the p-values, and we'll look at, you hopefully get very good at propagation of uncertainty. So we talked about that in quant. We did it in PChem a little bit. We'll come back at it your 3rd time. And typically it's the 3rd time you cover a piece of material that you really get it. So even if you didn't like that and you're like, oh, dang, I hated uncertainty, you know, propagation of uncertainty, don't shut yourself down, because it's the 3rd time you've seen it, so you'll probably get it this time. You're like, what was my problem? you know. And so I know your problem was those PChem labs were long, and it was at the end, and you were like, I don't have time for this. So that was your problem. Okay, so you'll get it this time, and so be positive. All right. So then the second part of the course is chemical evidence and then physical evidence. So if part of the quality control, let's talk about that a little bit. You're not alone in forensic science. You know, you're not just dropped into a lab and told, okay, come up with this analysis or learn these results. There's training requirements. There's all kinds of accreditation requirements for a lab to be able to do forensic analyses. And part of those accreditations are the technician's training. And so you'll be trained on any kind of instrument or any kind of method that you're asked to do. And that's also important too, because those methods have to be acceptable to the court system. So you can't just come up with a brand new method and start using it. The forensic community has to kind of bless it as being reliable, okay, and well known. And so what is that forensic science community? These are the organization of scientific area committees for forensic science. And they used to be called scientific working groups. And so you had SWG, like drug, SWG, photography. So you had these different scientific working groups, and now they've kind of switched over to these OSA committees. But look at all of the varieties that we have here. You know, we have, let's see if this laser works today. You know, we've got, nope, I think my battery's dead. That's okay. You know, over here in the chemical and instrumental analysis, we have toxicology, seized drugs, materials. You know, that's things that are not controlled substances, like materials might be glass from headlights. You know, so you've got a collision, and you can look at the materials and see if this glass came from this vehicle. There's enough trace elements in glass that you could tell the difference between different groups of manufactured cars. Geological minerals, so clays, soils, and a footprint or on a boot, you could analyze those things. There's a scientific, you know, working group or scientific area committee for those geological materials. Getting up to DNA, you don't just have human DNA, you also have wildlife forensics. Is that important? Well, poaching, you know, poisoning. So you have lots of things that you could do for wildlife, and that's pretty cool too. If you get your forensic chemistry degree and yet you're also an outdoorsy person, maybe you could find your way into the, when I say competitive could mean that there's a whole lot of people going for one goal, but competitive could also mean that there's only one or two spots, like only one or two chairs. So even if 5 people are going for those 2 chairs, it's competitive. And so there might be only 2 chairs in the room that are the wildlife forensic expert, but that may be you. And so that's kind of cool if you're, you know, again, a wildlife person. Over here we have digital media. We have a whole, I think, did we get a PhD in digital forensics now at SAM? I know we have a master's program. But anyway, digital forensics is a big thing here in our computer science area. Facial identification, even voice recognition, so all of the digital multimedia. We have crime scene and death investigation. Even like tooth impressions and so on. And then pattern evidence, tires and footwear, firearms and tool marks. So there's a whole committee just for firearms and tool marks. And there's a whole committee for footwear and tires. So, you know, once you get into your career, you know, you might want to serve on some of these committees, and that would be really a great experience. Okay. But initially, you'll be using the results of these committees to do your training. All right. Any questions about any of these? Did you know this? It's pretty cool to know about all of the different organizational assistances that you have. So let's talk about 3 key legal concepts that constrain us. So this glove that's on science, what are the 3 main cases that constrain us? And the first one was the Fry Rule. It goes way back at 1923. So evidence produced by scientific analysis is admissible into the courtroom if the techniques are accepted by the relevant scientific community. And what we just talked about is the relevant scientific community. So those scientific committees would evaluate these techniques and say, yeah, these have risen to the level of quality that we would accept them to be used in the court of law. And there's also legal precedent. You know, once it starts being accepted, by judges and so on in the court of law, then you start to see it has a pedigree of being used, and then you have the ability to argue for its use. And so you can accept this committees would look at the peer-reviewed literature to look for things like error rate. You don't want an analysis that gives a lot of false positives or false negatives. You don't want to have the innocent be locked up or the guilty go free. And so here are some good sources for the peer-reviewed literature. So if you're ever curious about any of these analyses, or if you're doing research and you're saying, wonder if there's a forensic application for the stuff that I'm doing in research, you can go into the peer-reviewed literature and look in the forensic journals and see. These are a couple, but there's a lot more. So this little link in the notes. Let's see, it pulls up like the top 25 on this one website. And so here we have the top forensic science journals and publications. And so this would be, great reading for you if you wanted to. I'm not hinting at that this is going to be, like, I'm not burying stuff in there for the course. I'm just saying this is on your own time. If you were curious about any of these, you could scroll through this, follow that link, and look at these. The nice thing when you see open access, that you can read all the papers. A lot of these, you have to have a subscription. So you can read the abstract. You can kind of see how the technique was used and so on, but you won't be able to get the full paper. But on open access, you would. So that's the Fry rule. So whenever you think of the Fry rule, think of the oldest case and think of the general acceptance, that a technique must be reviewed by peer-reviewed committees and accepted generally. Then they tightened things down a little bit in the early 90s. So Daubert versus Merrill Dow Pharmaceuticals. And this set out some more tight rules of evidence. And this set up the judge as having the gatekeeper role for admissibility. So basically the legal teams can argue for and against, and then it's the judge's call whether something is admissible or not. And if a case has a lot of evidence from these types of analyses, they'll have a separate hearing called a Daubert hearing before they start the trial, or maybe in the middle of the trial they'll stop things and do a Daubert hearing, and they'll go through and say, yes, this is admissible, this is not. So that it's not after the fact. You don't present it, the jury hears it, and then they say, I object, and you've got to tell people to forget what you just heard. That can cause a mistrial. So you can settle these things beforehand, and the judge is the one who says yes or no. And this is where you get into some of the details like error rate and peer review. So whenever you hear a Daubert decision, think of rules of evidence and think of the judge being the gatekeeper role. And this is mostly for scientific results. So these three cases are testable material. I would like you to know these because they're so foundational. And they are really restrictive in terms of the practice of science in the legal profession. And then we have this Kumho Tire case, 1999. And it extended Daubert to all expert testimony. So maybe you don't have scientific results, meaning empirical results, GCMS data or biological residues, but you have criminal psychology. Okay, criminal psychology, it's not necessarily going to have false positives and false negatives like a GCMS would. Okay, so this case extended Daubert to apply to all expert testimony, which means just that the judge has more power to decide whether something's admissible or not. And so how would a judge decide if a forensic psychologist was peer-reviewed? It's easy to look at a GCMS technique and say, yeah, this has been used in 400 cases, it's peer-reviewed and there's precedent. But what about a criminal psychologist? There's not a false positive rate on criminal psychology. So what would a judge use for that? Prior cases, experience, credentials. So the judge, there's still things that judge can use to decide whether he's going to allow this expert testimony or not. If we get a new graduate from our criminal psychology department. All of a sudden they're pulled in. They've never worked any cases. Yeah, they've got a degree in criminal psychology, but very little training in the actual practice of it. The judge probably would say, you need to find a different expert. I'm not going to allow this person to come right in and do it. Okay, so those are the cases. We have this. Have you heard of the CSI effect? That's something worth talking about. So describe to me what I mean. If you were to hear a CSI effect, what do you think of when you hear that?
It's like what people perceive forensic science to be based off of TV.
Okay. And what is it in TV that they base it off of? What do you think?
It's like in CSI where they go, like the person who's analyzing goes to the crime scene, pulls a piece of hair, goes back to the lab, analyzes it, and then tells you that it's a specific person.
Yeah.
And then that's not how it works at all, but people have the concept that that's how it works.
Yes, that it's that fast, okay, and that it's that straightforward, and it's that individual. I think that's probably the number one thing that they expect the results to be so clear that as a jury they really don't have to make any deliberations. This ought to be so clear this person did it. If it's not perfect, if they don't have the DNA and the hair analysis that says it's them, there's because in the TV shows it's all perfect. I mean, there's very little, most of the time they confess, so it's not even any deliberation. It's not that clean in the real world. Every case has unanswered questions. That doesn't mean that every case is wrong, that we're getting the wrong people all the time, but every case has unanswered questions. And so the expectations of the legal system, both the legal system and the lawyers and the jurors, have been impacted by the CSI effect. They watch these crime shows and they think everything ought to be cut and dry. And so it's very difficult now when you don't have all those scientific results or they're not that perfectly clear to make the case. Now, that's not really the forensic scientist's role. That's the legal team's role. But you realize that your results are going to be scrutinized and that they're going to want your results to be perfectly isolated to one person. That's probably not going to be the case, okay? Unless you're in DNA, where you're talking about 1 in a billion chance of it being someone else, So. And so then we have this different types of evidence. We have inclusive and exclusive. So inclusive, my blood type is A positive, and if they find A positive at the scene, then I'm included in that group. If they find O negative at the scene, I'm excluded. And so we're sort of dealing in yes or no questions. We like those kinds of yes or no questions. You're either included in the group or excluded from the group. The Venn diagram, you draw the circle. You're in the circle or you're out of the circle. And once you draw enough circles, blood type, skin color, hair type, etc., then it starts to isolate and individualize. But each one of those is a yes-no. And so those are the best types of analyses. It's either yes or no, in or out. And that's what we mean by inclusive or exclusive. And then we have direct and indirect evidence. And there's somewhat a prejudicial attitude against indirect evidence. Direct evidence is eyewitness testimony, and that's it. Okay, indirect is everything else. And you might have heard people say, well, they only had circumstantial evidence. And circumstantial is another way of saying indirect evidence. Okay, but most of probably all of your analysis is going to be on the indirect evidence side. And judges tell the juries there is no difference. You cannot put a higher weight on eyewitness testimony and a lower weight on indirect evidence. And why might you think that'd be the case? I mean, I saw him do it. What do you think?
There's been a lot of recording just people being directed towards picking out a certain person that didn't actually commit the crime.
Yeah.
And it can be inaccurate. You could think you saw something in the moment, but you see something that was actually different.
Yeah. And so even though someone really comes across as confident in the courtroom, they're still people. They still make mistakes. They may not be honest. You really can't tell. So you might say you want to weight, direct evidence lower than indirect, but we don't want to go there either. So the only option is to say they're equal. right? So that's sort of the safest option to say, look, we're going to look at the GCMS and we're going to listen to the testimony. And if that's all you had, and it was 50-50, you'd really be in a pickle, or blood type or something like that. I say he did it. I saw him do it, but his blood type isn't right, And so now you've got a situation where you've got exclusive evidence and you've got direct evidence that contradict each other 100%. And what can you say? You've got to weight them equally. So that's why we have to have at least 3 techniques in the lab that correspond, that aren't related to each other. So you may have to do an FTIR scan and a GC scan that gives you retention time. And then if you have a hyphenated technique like mass spec, that counts as a 3rd technique. And so if all 3 of those give you the confirmation of your result, then you've got 3 techniques in the indirect side, and then that can outweigh, say, a direct testimony. Okay, so it's 3 to 1. So those are some things that we deal with. And then you have destructive and non-destructive testing. We like non-destructive, but sometimes you just can't get around destroying a sample. Acid digestion is destructive, okay? Grinding and dissolving and so on, and maybe you could recover that after the fact. But again, the real key is how much sample will be destroyed. And this is where some of the uncertainty comes from. So, if you've got an object that you need to sample, a piece of fabric, the larger amount of fabric that you sample, the more confident you're going to be in its composition, but that also means you're destroying the evidence. So it's a balancing act between using a large sample to give you high confidence versus using a small sample so you don't destroy the evidence. So it's a pendulum. And then the most important thing with evidence is chain of custody, because it doesn't matter how confident you are in the results if you've lost track of those samples. If they went missing for a while, they were checked out of the evidence locker and then didn't get put back. There's a famous story in Los Alamos, this guy that got in trouble. He had a classified hard drive out after the time it was, closing time, put it back in the safe, and so he stuck it behind a copier. And so they found this classified hard drive behind a copier. It was bad. Okay, he got in a lot of trouble. And so this custody form follows each piece of evidence. It's checked out of the evidence locker. It's put back in. At the end of the semester, we'll take a tour of the Huntsville Police Department, so you can kind of see their operation. And you'll see they're in an old bank building. We passed a bond election about a year ago, and so they're building a new police department out on 2821, that road that goes by the new county jail. I don't know if y'all been out on that road. It goes to the high school. So it's going to be a really nice new police facility. But they're still in the old bank building downtown. And so the vault of the bank is their evidence locker. Yeah. And it's pretty bad in there because they don't have a lot of space. It's just, it's organized, but it's crammed full because I don't know what the requirements are, but they keep the evidence for a long time. They've got a whole wall of handguns and rifles and everything, guns that were used in crimes. For a while there, I think they finally got rid of this, but for 2 years there, you could almost not stand it. You walk in because they made a huge pot seizure, and then it was in their evidence locker, and the whole place smelled like marijuana. All the students that go in there like, whoa, Now, not like marijuana smoked, but like marijuana decaying, like getting old marijuana, and it was nasty. And so they had an air purifier in there, but it didn't really, it just wasn't keeping up. But when you come out of there, you're like, man, my clothes, they don't smell so good. I hope I don't get pulled over. So, yeah. And so then we'll get into the chemical evidence. So that was the quality part. Looking at the chemical evidence, we'll spend a lot of time on sample prep, liquid extraction. So go back to the organic days. We have the organic phase and the aqueous phase, and changing the pH of the aqueous phase will drive things into or out of the organic layer. So you'll get really good at that. Because a lot of times you'll have a mixture of analytes, you put it in the aqueous phase, and you want to pull one out and leave the other two there in the aqueous phase so you can analyze the organic phase, say in a gas chromatograph. It's real simple to do. You know the pKa's, you know, morphine or heroin or whatever, and you change the pH of the aqueous layer into the organic, the one you want goes, and you pull a sample and put it in your vials, dilute and shoot. Okay. And then colorimetric tests, and then all the different schemes for making drugs, like making meth or making heroin and so on. We'll get into the organic chemistry a little bit and look at the way those drugs are made. And so we start with this general unknown. We have presumptive tests, like spot tests. So like it's a GLP, a green leafy plant like material. And so you can take that and say, well, you know, this might be marijuana. So you grind some of it up, you put some ether in there, extract the THC and the CBD oils and so on. And then you can put in a couple of reagents and see if it turns a certain color. And if it turns that color, then that's a presumptive test for marijuana. You haven't proven that it's marijuana, but you've got the right color. And so that counts as one of your 3 tests. That's a presumptive test. And then you do screening tests. You might extract that material and separate it. Separation might be, again, on a GC or an LC, where it comes out at the right time. Test number 2, right? This is the retention time for CBD, and I got one of those peaks. And it should come with 2 THCs, and I got 2 other peaks. You know, maybe they're not resolved, but they're next to each other, and it has the same sort of retention pattern, the same chromatograph as what I expect from my standards. So I got a marijuana standard, and I run this green plant-like material, and I get the same kind of chromatograph. So now I've got a color change, and I got a chromatograph. Now, chromatograph doesn't really tell me what the molecule is, okay? It's the retention time. I mean, it could be something else. And so then you do these confirmatory tests. You know, and it depends on the substance. It might be an IR, it might be a mass spec, but it's going to be something related to the molecule. Okay, and so then you get down to actually testing the actual molecule and saying, yes, that was THC, that was CBD, and then you know. Okay. Then we get into the physical properties, physical evidence. So this is, again, like gunshot residue. There's chemical parts to gunshot residue, like there's lead and bismuth and antimony in the primer formulation. But then there's also the physical shape of those particles, right? This is a hot molten metal that comes out and then cools and then lands on your clothing or on your hand. And so we look at that under a microscope. And we'll see, yes, this person has these little metal oxide particles that are spherical in shape, which comes from a molten particle blowing into the wind. And so that's a physical effect. But again, that's evidence, okay? And so you can look at these little particles. They look a lot like pollen. And so determining whether a GSR is pollen or GSR is a key, and you need to use a microscope for that. Pollen is definitely not molten. And so we'll see when we get to that. Pollen has all these little spikes on it that if that particle was molten, those little spikes would melt. And so you can really tell, once you know what you're looking for, between pollen and GSR. Because GSR is smooth and pollen is pokey. Why would pollen be pokey? Yeah, so it attaches to stuff, you know, and animal fur and things, walking through and spread that pollen around, you know, bee behinds, and it goes and sticks it in another plant. And so then we get into arson evidence. You know, what do we see physically from an arson? What's indicative of arson? We get into color changes as well. Looking at alternate light sources, where we come into a room and we want to see evidence that we can't see with visible light in our eye as a detector. We might put special glasses on and shine a different color light. I'll bring some of those down here. I've got some UV lights and a green laser, my Raman laser, that fluoresces a lot of things, which Robin has verified. A lot of the stuff fluoresces, especially well with that green laser light. So we'll put on some glasses and we'll shine that laser light around, and we'll see how absolutely disgusting our keyboards are. So there's a lot of evidence on that keyboard. So it's terrible. Yeah. In fact, it would be too much. You know, you're like, there's 1,000 people now are our suspects. So probably not very good for individualization. Then the physical properties of polymers and fibers. You know, so looking at those 3 fibers in the middle, that's a physical effect. And so this is where the chemist has a problem. you trust your chemistry, right? You say, hey, I put this fiber on the FTIR, squeezed it down, it's polyester. Okay? And that was at the crime scene. And guess what? There was a fiber on the suspect's pants leg. We squeezed it down, it was polyester. Same fibers. Right? Chemically, they may be the same. But there's a physical side of things. If you don't look at it under the microscope, you can really embarrass yourself. Okay? A lot of times IR will test the base material, but it can't test the color because your eye is very sensitive to small color changes. And so you might put in 1 part per 1,000 or less of the colorant material, the dye, and IR is not going to detect that. You think about the IR peak from the polyester, the sort of carbonyl stretch, and let's just say if it's all the same signal, but your dye is only 1/1000th, then the peak from the dye is going to be 1,000th of the size of that carbonyl stretch. You're not going to detect it. And so you say, those were the same fiber, and then the defense says this one was red and this one was blue. And you look like a fool, right? Because you said they're both polyester, and they were, but you can't say they were the same fiber without looking at other physical properties, the color and the shape. Look at the top one and the middle one. They both have 3 edges to that fiber. It's a triangular fiber, it's extruded, but the top one has these little bumps on it and the middle one doesn't. Okay, so even if they're the same color, maybe they have a different profile. And so microscopy is something that forensic labs use a lot more than chemistry labs. The water quality lab really, it's not much need for a microscope. Maybe if you have some kind of residue in the water or something, but forensics uses microscopes a lot. Okay, and then there's another part of the course, that's work ethic. You're about to leave here, okay, and your flexibility in your schedule is going to evaporate. I know, it's sad. And I've had that experience too. I worked in industry for 4 or 5 years, and it was horrific. I mean, 10 days vacation, that's nothing. That's only 10 days in the whole year. But that's the real world in terms of the workplace. I mean, the academic schedule is great. How long did we have for Christmas? It was over a month. Yeah. And so I feel you. When you leave, you're going to be happy that you graduated, but there's going to be a little bit of sadness that you're going to have a routine up every morning, and counting out your little days of vacation and so on. It's so sad. Yeah. So as soon as I got a chance, my wife was like, get back into academia so we can cruise around in the summer and, have a long Christmas break and so on. So the lifestyle is great in academia. Not that I'm making a commercial for it, but I'm just saying that it's going to be sad when you leave and you realize every day, and you don't have this nice break at the end of the semester. There are no semesters. So we have closure. Like last fall, I don't care how good or bad it was going to end in December. And it was over. Whether, you played your role and you got what you got, but we're moving on, And that was a great feeling about academia, but it's, you have overlapping projects. You might finish a great project on Tuesday, but there's another one due Thursday. And, it just never seems to end out there in the, 9 to 5 type setup. But the other nice thing is that 9 to 5 setup, when the bell rings at 5, you leave it at work and you walk home and you don't have to take it home with you. Now sometimes you may want to improve yourself and do some more training and so on. So there'll be some evening work, but you're calling the shots on that. It's not DW's stupid homework that's doing it. But my point with this and this little lecture is to say I'm trying to build a ramp for you as you move into industry to have things that you do every day and to have things that are due every week, because that's going to be the case. There's going to be some kind of things that you have to do once a day and once a week, once a day and once a week. And so that's part of this control chart exercise. It's not so much about the data, it's about the work ethic. And not saying, okay, I won't do anything for 3 days and I'll catch up on the 4th day. Because you can't do that sometimes. If you're tracking an oven and that oven is relied upon for a certain set of analyses and you've got to write the temperature down every day, you can't just go 4 days and then write the temperature down. you know, and one, you may be lying about the previous 3 days, and that's bad. Okay, ethically it's bad. 2, it'll get your rear end fired. Okay, and 3, you'll really embarrass everybody in the whole lab scene because they've got to take all the analyses that were done on those 3 days and throw them out and redo them. And then they got to tell the legal team, you know, those results we gave you, those are invalid. Give them back, and we got to redo it. And that's not good. It's horrible when you have to do a daily task and you haven't done it, and then you've got to throw out all of those analyses. You will wish you got fired. So I want to do this again with the homework and the control chart. So Tuesdays and Thursdays, I kind of broke it up so it's not all due on one day. And so Tuesday nights will be the control chart, Thursday nights will be the homework, and we'll just every week, and the control chart will be every day. But we are human, there's human nature involved, so I want your data to be something that you can go back and look up if you missed a day, okay? So your data should come from something like an internet resource. Like if you're doing weather data, you should be able to pull it off of some sort of weather site. If you're doing stocks, you know, you can go back and look at the history of stocks and so on. But still, I want you to get in that habit of doing something every day. If you're going to do something like tracking number of steps or whatever, you need to have a way that if you miss a day that you can get that data, that it's recorded for you. I had a student measure how long it took her dog to find a spot in the morning, okay? You know, and I approved that one, although that's risky because she can't look that up, you know, if she missed a day. But she's not going to miss a day because her dog's going to pee on her floor, you know, so she's, right? I mean, so that was kind of an odd one, but it worked, okay? And so I had a whole control chart the whole semester, how long it took her little dog to pee in the morning. And it was kind of interesting. But, you know, it was in control, you know, but like 25 to 28 seconds was the average, you know, plus or minus. And then it'd be like 2 minutes. And we're like, what happened to your dog? She's like, somebody was walking along the sidewalk and he had to bark. You know, and so, but what was interesting about that was it was in control until something unique happened. So that turned out to be one of the best control charts because, again, that dog had a rhythm that was more or less an average plus or minus some random variation, you know, whatever that dog's looking at in the grass to decide that's the spot, you know, was in control the whole semester. And unless there was some external or unusual event, like a person walking by, then the system was out of control. And that was a good example of your oven's working fine, you know, it's got the same temperature every morning, plus or minus, until some event happens, like you lost power that night because of a thunderstorm, and then it came on 4 hours later, well, that oven cooled down. And now when it came back up in the morning, you know something happened. That was a unique event. So that's what you're looking for in your control charts. You want your control chart to do nothing. And then when there's something unusual, you want it to do something. You know, so it'll be in control. We'll take 15, so 3 weeks of data, so 3 5-day collections of data, and that will be what we call the training period. So we're getting used to how the system works. And so once we have 15 data points, so after the 3rd week, then we'll do the average and standard deviation for that behavior. So we're learning the process. I call it training. We're not really training the thing that we're analyzing. We're training our expectations. So the system's telling us how it behaves for 15 days, and then we have the average and the standard deviation. And then from that point, those average and standard deviation, we do not change those. We say that is what we define as in control. So if it's hovering around that average and within the standard deviation for the rest of the semester, then it's been in control the whole time. So the first 15 days tell us what control means, and then we track it to see if it's in control the whole time. Now this is why we can't do temperature. A lot of people say, well, I'll just do daily temperature, because what's going to happen, hopefully, as we go into April and May? Yes, that's not in control, right? It's moving. It's got a slope to it. A control chart should be flat. It should be the same every day. Okay, so we need to figure out a way you can do temperature differences. So we can take today minus yesterday, and that will hover around 0. Some days it'll be high, some days it'll be low. You know, today minus yesterday might be negative in case we had a cold front come through, but then it's going to get warm again, so it'll be positive again. And so daily differences if it's got a slope, you take the derivative of that slope, it's fairly constant. It's going to drop to 0. Okay. And so we can do daily differences on things like temperature, barometric pressure. So whatever you kind of think of, I need to approve that. So we'll look at some of the control chart data here in a second. So there's the control chart assignment, and again, you will tonight upload your idea for what data you're going to collect. Okay, and this is some people deliberate over this like they're choosing the color for their wedding or something. It just drives me crazy. So just pick something. All right, I know it's something you want to like it. I mean, to some degree, be somewhat interested in it, but it's not that big of a deal. Okay, it's more important that you pick something that's continuous, that you can track every day. Okay. So let's look at, this is sort of the control chart. The first 15 days are the training period. And so then the mean, the plus or minus 1 standard deviation is the watch limit. And then plus or minus 2 standard deviations is the action limit. And so it'll be around 5%, 2.5 high, 2.5 low, 5% chance of being outside of those limits. So, 20 data points, you're probably going to get 1 out. If it was perfectly, sampling the whole range. So you should have something to say by the end of the semester. This one had 4 data points that were outside of the action limit. And so our action in this case, like if your oven was out of control in the lab, you'd have an action limit that actually did something with the oven. Maybe one is to investigate, right? Oh, we lost power last night. You write that in the logbook, and you see if it comes back to its average behavior the next day, and you say we're good. Nothing broke on the oven. The other option might be the oven did break, and you look at it and you go, oh wow, the heating element is old for whatever. Most of the time they just go out. But let's just say it can't maintain the temperature, and so then you would replace the oven. That would be your action. But we're not really going to have those options. You're tracking a stock market. What are you going to do? Call up Yamaha and say your stock is bad, right? I mean, you can't control that system. We had a guy track Yamaha motorcycles. That was pretty cool too, because that was when the Japanese earthquake happened and everything. And I mean, that stock went berserk. It was in control, and then all of a sudden it was like, and then it quit for 3 weeks or something because of the tsunami. Yeah, it was very interesting. So you never know what's going to happen. So these 4 out of the action, when it goes out of the action limit, your action is to make a log entry. And so you'll have the data procedure, what you do with the data in your little report, and then you have the control chart, and this is again a month down the road, and then you'll have an action log. And if it's never out of control, then you don't have any entries. But if you get one that's outside the high or low action limit, then you make an entry and say, like if you're tracking stocks, tsunami hit the country. You put that in there on such and such date, and you might put a reference, like if you got a website from that. If you're doing temperature and you get a huge negative daily difference, you say, well, a cold front came in on such and such date. Put your, web link of where you got the data. Had a person tracking their daily difference in weight, and so every day they would weigh on the scale and they would write it down, and they got the flu. It's pretty interesting. So they're in control, and all of a sudden it was like negative, 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 and they were out of control. Definitely out of control. They got the flu, and they lost weight. Not recommended way to lose weight, but it was trackable. Because they were going along. It wasn't a lot of weight, but it was out of control. So that was pretty cool. And so if you're tracking the differences, it's always today minus yesterday, because we want the signs to be correct. If today's higher than yesterday, we want it to be a plus sign. And if today's lower than yesterday, we want it to be a minus sign. So this is not correct. Yesterday minus today would flip the signs. And so if today is bigger than yesterday and you do it that way, then it's a negative number. We don't want that. Mentally, we want, if it goes up, we want a positive sign. If it goes down, we want a negative sign. So this is really important. It's the number one thing that people lose points on when they do differences, is they get the order switched. And then they also don't use the English correctly. So how would you say this? You would say that, I want to make sure I get it right? So they would say in their English, in their sentence, they would say the temperature for yesterday is subtracted from the temperature today. See that? So the temperature from yesterday is subtracted from the temperature today. So that's how you would say it. They'll swap that language and they'll say it one way and then the equation will be different. And so the equation and the English have to match. So pay attention to that. Okay. Gas prices are not good either way. So nobody track gasoline. Okay. And I'll show you why. So we've kind of talked about this a little bit. This is what your spreadsheet will look like. You'll have that training period and no graphs. So at the beginning, you just have 5 sets of data for the first week. 5 more points the next week, 5 more points the next week. And that's all you're turning in is your Excel sheet for the first 3 assignments. Okay. Then you'll turn in a graph. We'll set up your limits. And so you'll take the average and standard deviation for those. So here we have the average of the data, and that's up there, the measured mean, and then we have the standard deviation of the data. And so those 2 cells are now fixed based on the training period, and they don't change anymore. And so then let's plot the limits. So then we create 5 columns. We have the average, and we have the plus or minus 1 sigma and plus or minus 2 sigma. And so those columns just have the same number all the way down. And it's kind of ugly in the spreadsheet. It's just, 0.48 all the way down. But you're just setting up the limits. And then you can set up an if-then statement that says, if my daily data is higher than the 2s, then it's high. If it's lower than the minus 2s, then it's too low, and we can trigger an action. So that's what this if-then statement is. So this is how you build your spreadsheet. So save this lecture. So when you're building your spreadsheet, come back to this lecture, and these are your formulas that you will use. Okay. And so we're using an OR function. If, or, and in either one of these cases is true. If D8, which is the data, is greater than H8, which is the mean plus 2 sigma, it is too high. Or if D8 is less than the mean minus 2 sigma, it's too low. So if either one of those is true, then, in quotes, beyond action level, it's either high or low, else, and then I have the little 2 quotes by themselves with nothing in between, and that just means nothing's printed in the cell. So this is beyond the action level, but this one wasn't, and so it doesn't print anything except when it's out of control. So that's a nice little formula that you can use. If you want to do 2 if-then statements, you could say above level or below. I mean, you have some freedom to do it your way if you want. And so for your alert log, this is an example of the log. You have the date that it was out of control, like 3:20. You say it was above the action level, and then it was, let's see, I'm trying to think of what this was. It just says they did some research that higher than usual building use on this day, but I don't know what that's related to. But you have some sort of statement as to what was going on. Like the person with this weight said, I had the flu for 2 days. So that's what went on for their out of control data point. Okay. Now this is what it should look like. Your control chart should look just like this, with these dates sideways so that they don't run into each other. With everything labeled, it says date here, whatever you're tracking here. You can do grid lines on the vertical for the date, so you can line up and see what date is what. I just did it once a week. You could do, anyway, you can, I'm not so picky on how many of these you have, just as long as you can read them and they're separated. Once a week is nice. The mean will be green. Then the plus or minus 1 standard deviation is yellow or orange, and plus or minus 2 is red. And so that tells you once you get outside the red, then it's, quote, out of control. Something special has happened because there's only a 5% chance of that happening. And so that's our 95% confidence. It's really close to 95. It's not exact. We'd have to use 1.96 instead of 2. But anyway, that's traditionally just use 2 plus or minus 2 sigma. And we have, a data point here that's outside of it. It's right above the line. And so we'd have to put an action log entry for that. But everything else looks good. Now look at the data. Do you see any patterns in there? It looks streaked. I mean, it looks, randomly varying to me. What about this? How would you describe this data? it looks wrong, doesn't it? Or does it not? I mean, this data should look wrong to you. I'm trying to tell you, yeah. And this happens sometimes. And if this is happening to you in your work, you need to fix it. So we'll try to figure out what it is that needs to fix. Any takers? What? Tell me what you see. What is it that's bothering you about this data? Go ahead.
Some of the points don't actually connect, they just sit next to each other. And it's like a double.
It's like you get the same answer multiple times. Is that what you mean? Yeah.
Like on, or between January 30th and February 6th, there's 3 dots, all in the same one. And I don't think that for the same day we could have 1, 2, 3, go up or 2, come back. Like, I don't know. That doesn't sound like a very accurate picture.
Yeah, so that's the question. What words do we use? Okay, and it's weird. This chart could be accurate. So that word isn't the word we're looking for, but you're onto something. We're looking for the word to describe this data, and it's called discrete. This is discrete data, meaning there's really only 4 answers. See that? There's only 4 answers. We want continuous data. So that's the thing that we're dealing with, discrete versus continuous. And we need a continuous data source. We need something that varies a lot, has a lot of decimal places to it. This only has 4 options. And this is what you get with gasoline prices, right? It'll stay, whatever, $2.39 for 4 days. And then it'll go up to $2.41. And then it'll come down to $2.37. And so we're dealing in cents, and since they're rounded up to cents or maybe even a tenth of a cent, it doesn't change enough. It's not continuous. So that's why we don't do gasoline prices. Now you could do some sort of averaging or whatever, but it just makes things complicated. So let's just take gasoline prices off the table because it ends up looking like this. This is when you start to see discrete data like this, then your statistical assumptions like standard deviation and the plus or minus, all those statistics that we're basing our decisions on break down. So we're using our action limits and saying there's a 5% chance of being out of control. That doesn't apply to discrete data. Okay, so this is a warning. If you see discrete data in a control chart, you need to change how you're tracking that system because the statistical assumptions that you have are based on continuous data, not on discrete data. Okay, the Gaussian distribution is based on continuous data, not on discrete data. So when you see this, then you've got a big warning sign. So remember this day. Okay, we're probably not going to come back to talk about this, but I mean really, put in your notes a big star to say our statistics are based on continuous data. This happened to us at my industry job. The technicians in the morning were told they had to check the balances to make sure they were working correctly before they did any analyses that day. And they would tear the balance, and if it didn't go to 0, they would mark it as out of control. Okay, so they were trying to control the balance to plus or minus a tenth of a milligram. Right, that last decimal place. So if it didn't read 0, 0, 0, 0, 4 places of zeros, then they would say it's out of control. So if it was just a tenth of a milligram off, air currents or whatever, vibration in the room, there's lots of things that can cause that to move, but it doesn't cause it to move much. It might go up 0.0001. Maybe 0.002, it's not out of control. But they would call the metrology group over to calibrate the balance, and the metrology group was like, this balance is working fine. Why are you marking it with a red tag and not working all day? So there's also an incentive not to work, right? I can't work, can't do my job, the balance isn't behaving, It's convenient, yes. And so, we figured out, let's actually exercise the balance. Let's put a weight on there, a 1 gram weight, and let's determine what uncertainty is actually impactful to our results. Right, if we're making a calibration curve and the best we can do with our serial dilutions is plus or minus 5% because of our pipettes, why do we need to hold the balance to 0.1%? Right, the balance isn't interfering with our uncertainty, and we'll get into that in detail with our uncertainty analysis. So we expanded the limits a little bit. So if that weight was off by 1 or 2%, then the balance was labeled out of control. But if it was within a decent set of action limits, then the balance was fine and they could work. You know how much money that saved the company? Add up all the technician time sitting on their hands with a red tag on the balance. It was $48,000. Yeah, and it was just a control chart problem because they were just trying to hold it too tightly, and it was this discrete data too. So plus 1 milligram was enough to throw them out of control. So it was an issue. Now this is like the temperature thing. So that's not in control because it's trending. So it's not one data point that's out. You see that the slope is moving towards the control limit and eventually will go past it. And so there's actually statistical control tests to say if the mean is changing of the past 5 days and it's always going up, then it's out of control, even though nothing's gone outside the action limits. And so this is what we're doing with control charting. It's called the Kanban process. It's a Japanese principle it's called pull. So we do this also in like Amazon and so on. Amazon's not going to order a lot of new stuff until people order a lot of new stuff. And so you order something from Amazon and then they see and they order something from their distributors and so on. So it pulls. That's different than a store that buys a lot of inventory and tries to push it. Okay, and so the pull process is if you're calibrating your instrument, you don't do anything with it until it tells you it's out of control. So the instrument pulls its own calibration. Now, not a lot of labs work that way. A lot of labs will still say you're going to calibrate every day or every Monday or something like that, but they don't have to. If they trust their statistics, they can calibrate on a pull process. They run a check sample, look at the control chart, it's still in control. Maybe they do a second check sample at a different range, say it's in control. So my 2 check samples are both in control, my high and my low. Don't jack with the instrument. Right? The instrument will tell you when it's out of control. So you show up in the morning, you run your 2 check samples and one of them's off. Okay, this instrument's telling me it's time to recalibrate. You can save an enormous amount of time if you're just running 2 check samples rather than making up a whole set of calibration standards and going through. And so that's the pull process, and we're still in the process of moving to that next level of quality where our instruments pull their calibrations rather than you pushing them onto the instruments. Because think about it, you think, well, it's always good to calibrate. No, it's not. What if you had the sweetest calibration and that instrument was working perfectly and you come in and that day you're off and you make your calibration standards worse than they were? So just because you calibrated doesn't mean you made things better. You might have made things worse by screwing it up, okay? And how would you know? You've got variability in your procedures and techniques. And so it's not always good to just recalibrate all the time. You're actually introducing uncertainty into the system the more you get involved. And so if you've got a system that's behaving well, let it behave well. But track it so that you know. So that's what we mean by pull or Kanban. Kanban is Japanese for sign. And so it's like a color change, like the instrument says, change me. Like the little, well, I was thinking of babies and diapers. But there's a sign, right, that says, okay, it's time to take action. And so with that, we're finished. We've covered so much, and we've talked about the control chart and so on. So I know you have some reactions and some questions. So what is it that's on your mind? What kind of data are you thinking about doing?
Or you could do something with stock.
Stocks, yes.
Wouldn't that also have a general trend?
Yes, so you can do the daily difference in stocks. And so if you're going to do stocks, again, they can trend up or down. And so just do today minus yesterday, and then you can see the differences. So even if they are trending, that difference will be canceled out. You say, well, what about a quadratic trend or something like that? But each of those little slopes will essentially be canceled out. What that will show up as then is a change in standard deviation. And so it's pretty rare, but sometimes we see that it'll be quiet for a while during a training session, and then all of a sudden the data starts to get noisier and noisier. And so by the end of the semester, you have a high one out of control and a low one out of control, and it's just large swings in the stock price. But it's okay, it's interesting, and it's always fun to kind of do research on what happened. If you do a stock, I would say pick a particular company, not like the Dow Jones or the NASDAQ, because it'll be much easier to research for that company what happened. Like, and stock splits too, like maybe they're $250 a share and the next day they switch to 125. And so then you're going to say, whoa, what just happened? We have a huge thing out of control, right? That's fine. You got an action. And so then you put in the action log, they did a stock split. And then so that the data jumped in half. But if you're taking the daily difference, the next day, the differences are going to calm down and you'll be back in control. Yeah, so I like stocks, and plus they're easy to research. And third, it's fun, because you're like, oh, I got to check the stock market today. Really? We're taking a business class? No, forensic chemistry. So there you get a few looks, but anyway, it's enjoyable. Yeah. And, there's one student, the craziest one I had, aside from the dog peeing, was this person played video games every day. Okay, and she had a mouse clicker, like counter, like how many mouse clicks she did on this game. And she would play and play and play and play and play, and she would have like her average was like 5,000, clicks. It must have been a shooter, right? And so then, she would like be out of control at 7,000 or something. And she's like, yeah, she had something to say in the log. It was really entertaining to read. So it can be, but I was like, I didn't like that one because I'm thinking, look, you got other things to do. And I'm encouraging this now because now you got to play that every day. So she played me, I think. She's like, nope, got to play my game because that's my class, So I don't know. That was the weird one, but it was fun. Yeah. So anybody else ideas? What you want about something? Yes.
For something like pressure, would you have to account for daily difference? Like if you were doing the pressure at an airport, like in your example?
It might. I think it. I don't know that it creeps up, but it does swing pretty far, like over days and so on. So I think it. Daily difference is better for pressure. I don't know that it's necessary, but it is better. It'll be more in control. And then you'll really only detect those significant events like a huge cold front come in. Yeah. Because you'll see a swing down to low pressure as that low pressure moves through, and then you'll be able to see like nothing cold front, as opposed to the other one, it'll be trending like this, and it'll be harder to detect because your standard deviation will be wider. And yeah. So I think daily difference is better. So if you're going to do pressure, yeah, let's do daily difference so that the number of out of control points is manageable. It'll be more realistic, I guess. Yeah. Yes.
And instead of like doing daily difference for like weather events, would you be okay with the difference between locations that have similar climates but slightly different?
Yeah, I guess both would trend up as spring came in, but the difference maybe, yeah, sure, that might be cool. But like you have two different towns or something?
Yeah, I was thinking of tracking humidity between Round Rock and here.
Yeah,
and looking at the difference between the two.
Yeah, because it's different. So what would you do? Since this is more humid, right? Let's track this one minus Round Rock, right, to see how much more humid we are than Round Rock. Yeah. So everybody's going to be interested in your control chart, really. So we can complain. Everybody likes to have that sort of badge of I can complain more than you. Yeah, so that'll be a good one. Yeah, and we'll see if it stays in control because I haven't heard anybody do that. Yeah. All right. Well, that's a great day, and there's something due tonight. Tonight is control chart day or homework day. Tuesday, control chart day. So tonight. There's a link on there to go in and CC01, that's control chart assignment 1. Give me your idea for your data track that you're going to track. So that's due tonight. Okay, so go ahead and let me know, and then I can look through those, and we'll see if there's any issues. Yes?
When are we supposed to start tracking data?
Let me look at the schedule. I think it's Monday. Yeah, because we need some time to we need to decide on what the date is. So let's decide by tonight. Tell me tonight. Then I'll have a few days to approve or adjust, and then everybody will start tracking on Monday. Okay, and if that throws us off a week, so be it. But let's make that decision. Okay.
How's it going? Thank you.